Hey guys, in this video we're going to look at the DCA75's capability of measuring germanium transistors. I've got other videos I'm going to do on the DCA75, but at this point I've spent a lot of time with the germanium transistor testing side of things, so I'm going to focus on that while it's fresh in my head, because there's a bit of technical details I've got to go through. Don't get too intimidated by this. I'm going to try and keep this as simple as possible. In fact, I'm going to avoid some of the heavier details just to keep things digestible from my viewers that aren't so technically minded, a bit like me. So let's have a look at what it can do. Now, a lot of people will say you just get a DCA75 or a DCA55. A DCA55 is the DCA75 with a few less features, and it doesn't do curve tracing. So you just get one of those, you plug your transistor into the device, you hit the on button, it tells you the HFE, you write it down, you write down the leakage, you move on to the next one. I don't think that is probably the best way to use a DCA75 to test the HFE for a germanium transistor, and I've found that it will give you, it varies, but generally it gives you a higher HFE value than what you would get if you used one of the more traditional manual ways of measuring a germanium transistor. What's a manual way? Okay, well, usually when it comes to germanium transistor testing, I recommend either the RJ Keen transistor tester or the small bear transistor, simplified transistor tester, and that's the one we're going to be looking at because it is simple. And it's the one that I've used pretty much majority of my pedal germanium transistor testing. I've always used the small bear one. It's always given me the result that I've expected. If it says it's high HFE, it sounds high HFE, generally, you know, roughly, it works well for me. It's what I've always used. So this is the schematic, and let me just explain what's going on here. So you have to excuse my rough diagram here, but this is effectively what it is. So you've got 9-volt supply, you've got that's a current meter to measure the current, and you've got, sorry I can't see from that side, collector, emitter, base, and the 1 meg resistor which goes down and connects to the base and the switch. Now what is this thing actually doing? Well, if we remove this part, let's say the switch is open, so the 1 meg resistor isn't connected to the base. So all we've got is 9 volts flowing through the transistor pretty much. Let's go with pretty much. Trying to flow through the transistor, and a current meter. This will tell you the leakage because some of that voltage, some of the current will actually flow through the transistor even when it's switched off. That's what leakage is. You will get, you know, let's just pretend you've got your 9-volt potential here. You'll have a little bit of current flowing through. So it's basically like the transistor is turned on all of the time, even when there's nothing flowing to the base. That's how a transistor is supposed to work. You're supposed to have something on the base to show a higher current on the collector. And with the germanium transistor, you can still have a current on the collector with nothing on the base, which is not what a transistor is meant to do. So that's how it's measuring the leakage. There's nothing on the base because that's not connected. There's no current flowing through here. That's open, but you still get a current flowing through here, and that's the leakage current. When you connect the switch up the top here, you close the circuit and you add the 1 meg resistor, you'll have 9 microamps on the base because you've got 9 volts. So if you know your Ohm's law, what's that? Let me think of the Ohm's law pyramid. This is the only way I ever remember. V, I, R. So it's, what are we after? We're after I. So it's I equals V over R. That pyramid. It's awesome. So the only way I ever remember these equations. So if you're after I, you pull it out. You just take it out of the pyramid. So it's I equals V over R. You can do it with anything. V. So if you want to, if you're looking for voltage, take V out. I times R. if you after R take it out, R equals V over I. It's very handy. Whoops, sorry. So yeah, so to get the current, we've got voltage and we've got resistance. So take the I out. Whoops, sorry about this shoddy diagram here. Take the I out, so it's I equals V over R. So that will be, I know this because I work with this circuit all the time, it's 9 microamps on the base. So when you've got 9 microamps on the base, how much current do you have on the collector? Well, let's just say you've got, let's just pull a figure out and let's make it easy, okay? We've got 9 microamps on the base and we've got 90 microamps on the collector. What is the HFE? Well, the HFE is a relationship, HFE as it is a relationship between the base current and the collector current. What is the ratio between those two measurements, the current on the base and the collector? The ratio is the HFE. So if it was 9 and 90, it would be 10. 10 is the difference. So you've got 10 times the amount of current on the collector that you do on the base. So the HFE for that transistor would be 10. So that's nice and simple, and it works well. As I've said, it will give you an accurate reading. The thing is, though, with germanium transistors, they change. It's not if you get the same transistor and you put one microamp on the base, you might find there's 20 microamps on the collector. So you end up with that's a different reading. It's not 10 anymore. Now it's 20. So you have to sort of set the conditions up in a way that is suitable for fuzz pedals to simulate, I guess you could say, simulate a fuzz pedal to get an accurate reading. The DCA just a standard set out test does not do that. The way the DCA measures HFE is it will put a base current into the transistor until it sees 5 milliamp on the collector. So you can see already that it works differently. With the small bear germanium transistor test, we know there's 9 microamp on the base. That's the known figure. With the DCA75, the known figure is the 5 milliamp on the collector. We don't know how much current is going into the base. It could be substantially more than 9 microamps, sorry, as with the small bear test. We just don't know. So you're getting a different HFE reading in a different situation. You don't know where on that curve the DCA is going to be testing. Does it matter for guitar pedals, for measuring fuzz pedals? You're probably going to think I'm going to say no, but I think it actually does, because it depends vastly on the transistor. Again, it depends how the transistor opens up, because the HFE changes as you apply. Every transistor is different, and it will change depending on how much base current you're pumping in, depending on the voltage supply that you've got across VCE. There's a bunch of parameters that make it different, that make things make the HFE change over those conditions. So I think a more accurate way is to actually use the curve tracing ability on the DCA75 to check the germanium transistor HFE. I know there's a lot of people that measure, the germanium transistors on a DCA55, done, yep, done, yep, and they're on eBay and they're kind of just pumping out germanium transistors, just testing one after another. Yep, done. Oh, I bought them for 30 cents. I'll charge $1. But it's not, I don't know if it's that accurate. And I can tell you with specific transistors, the difference is double. You get double the HFE off the quick test that you do with a simulated small bear test. So what we'd need to do to simulate the small bear test is to try and get approximately 9 milliamp on the base, and then measure and then take our measurement, which is relatively simple to do with the curve tracing ability of the DCA, and which is one of the reasons why I think the DCA75 kicks ass, is because you can do that. It can do a lot of different things like that. So let's have a quick look at an example and just some of the measurements I put into the DCA75 to get the correct, I hate to use it, but correct readings. It's not really correct, it's just my method of doing it. I think it's more accurate, and I've checked it against some of the previous transistors I've tested with the small bare manual way of doing it, and they're almost spot on, within 5% of what I've measured before. So I'm just going to sift through some of my massive hoard of transistors and pick one out that I know that I recorded with the small bare test. There's a lot of factors involved with germanium transistor testing. There's temperature, there's the conditions that they were tested at. It's part of the reason why I think there's a lot of confusion with them as well, because you see people that have bought germanium transistors on eBay or whatever, and it says, oh, they've got a HFE of 100, and they test it and they go, no, it doesn't, it's got a HFE of 20. You ripped me off. You sold me something that's not right, but that's not how it works. Sorry, I'll try not to handle that transistor too much. So this is what I've tested previously. You can see it had a collector current of 509 with a leakage of 61, so you have to take 61 off 509, and that will give you, if you do the calculation, it'll give you 49.7, which is pretty specific, but yeah, 49.7 HFE. So let's just test it on this with the curve tracing ability. I'll just hook it up. So I haven't got my screenshot screen capturing software set up. You'll have to forgive the camcord view. So on this, you can see when you first plug it into the DCA75, if I can get the camera in the right spot, it's going to have to be close enough. It will do its quick test, and it says over here it's detected a PNP germanium, and it tells you the pin out, which is incredibly handy, particularly if you're dealing with all sorts of different transistors. It will tell you the pin out. I've killed many transistors by not knowing the pin out properly and hooking it up the wrong way, and killing one of the junctions. And it says it's got a HFE of 70. Whoa, hang on a sec, 70? But I thought it was supposed to be 49.7. Why the substantial difference? It's because of what I was saying before. And the leakage is 51. My leakage that I tested was 61. I find the DCA gives you a slightly lower leakage, and there's a reason for that. So what I usually do for testing is go to HFE over IC, and down the bottom here you can put in whatever. I hope you can see that. Let me just zoom into that section. So down the bottom there you can see you can put in whatever parameters you want, and as you can probably see now, you can put in whatever HFE you want there. I usually go 4 and 9 because 4 is a very rough simulation of RG Keen's circuit. RG Keen's circuit works a little bit differently. It's a little bit more complicated. So it's very rough, but it shows you probably the minimum HFE you're going to get out of the transistor, whereas 9 is more a small bare simulation. And then you want 2 points, so you're going to have a point at 4 and then a point at 9, and then 9 volts, a 9 volt supply, 9 volt VCE. Because, as you can see, as you might be able to see in a moment when I move the camera, over this side, you've got a 700 ohm resistor, a load resistor here. So VCE is actually from voltage collector to emitter. Doesn't include the load resistor of 700 ohms. So you need 9 volt VCE. Not 9 volt supply, not 9 volt VCC, 9 volt VCE. And if we run it, sorry, I forgot to change that to 1 trace. You want 9 volt 1 trace, then you go start, and you will see it gives you 2 measurements. One is at 40, approximately, just over 40, and the other one is at 46. And what was mine? 49. That, to me, is a much more accurate way of testing a germanium transistor than just whacking it in and press button, which I know a lot of germanium transistor sellers do. So does 20 HFE make that much difference for a germanium transistor? Do we need to worry about it? I think for this case, no, I don't think 20 HFE is going to make a world of difference. It's not If it was 20 HFE compared to 100, yes, that's quite a substantial difference. But for this one, it's not that big a difference. But some do. Some have more than double, report more than double HFE. Some will report a 200 HFE, and then you test it with the small band method. It'll come back as 80 or 90. There's quite a big difference in that respect, and it will sound probably different. But there's so many factors involved with measuring the germanium transistors for fuzz pedals, and people tend to stick with the RG Keen recommendation of what HFEs he recommends. I wasn't going to explain it because it's a bombardment of information, but you're looking about 70 to 90 Q1, and then 100 to 140 for Q2. Approximately, but he also says over 140, so 140 to 180 is cool as well. It gives you a bit of a different sound, which is also what I've found. But some transistors don't act like that. I've had 40 HFE transistors in a fuzz face I was actually just testing the other day, and it sounded phenomenally good. It did not sound like a 4040 transistor. There's a lot of factors going on. You've got a trim pot in there that you can change for the collector, assuming you've put a bias trim pot in your fuzz face. You can change that, and you can put one on Q1 and Q2. You can change the emitter potentiometer for the fuzz dial. You can do all those sorts of things. You can adapt your circuit to the transistors that you're using to make them sound good, and that's why I've said in the past that I think frequency response is just as important, because you can sort of adapt. Even 10 HFE transistors sound good when you Darlington them together, and I'm going to do a video on a Darlington fuzz face and show you what it sounds like. It sounds pretty good, even and that's at 350 HFE. It doesn't sound like, it doesn't have a typical fuzz sound. It sounds probably more like a distortion, but it still sounds good. So it's science and art, I guess, combined together. But I want to start with a measurement that I trust and I know and I'm familiar with, and that's why I do it this way. I suppose if you're going to just test your transistor straight off the DCA, it's not going to hurt anyone, and you'll get used to the readings it gives and what's acceptable and what's not. But I always provide the specifications when I measure a germanium transistor. I write down on the sheet what I measured so that you can see what I actually measured. And the one that I'm familiar with is the small bear test, which calls for, as I said, 70 to 90 approximately for Q1 and 100 to 140 for Q2. Even I'm a little bit loose about that sometimes. If I get 48, I'll still include it. It's not that critical, but it's got to be around that sort of range. So anyway, I hope that was an interesting look at germanium transistor testing with the DCA75. I've learned a lot from it myself, and how transistors react with different properties. That's one of the things that I mentioned in the overview of the DCA75 that I liked the most, was that you can visually see what happens to a transistor, how it reacts to different conditions of the circuit. And I've learned a lot from that. It's kind of like taking a 3D view instead of just a 2D snapshot of on a multimeter. Bang! This is the result you get. You can actually see how it reacts. And sometimes you get an odd transistor that is behaving very, very bizarrely, and you can just say, well, I'm just going to pump up the base current and see what happens on the collector. And you pump it up and you go, oh, okay, it doesn't actually turn on till much later on. And it requires a lot more power to open up the transistor. Learn lots of things like that. So it's not just a fast way of measuring germanium transistors for me, the DCA75. It's not even just an adaptable way of measuring germanium transistors. It's also a bit of a learning tool and a discovery tool as well. And that's why, if this DCA75 exploded in flames tomorrow and I needed a new one, I would go and buy one, because it has just changed the way that I've seen germanium transistors and how I measure them. Thank you very much for watching this video. I hope you may have learned something. If you've got some comments, your opinion on how to measure germanium transistors, how you would differ from my approach, and any other information that you want to put down, please feel free to. Might leave some links in the description of this video, just so you can read a bit more. The small bear link, the link to the small bear schematic, the link to the DCA75 of course, and things like that, so you can do a bit more reading on the topic. But that is it for this one. Thank you very much for watching. Appreciate all your views and your comments. Bye for now.